I promise you some computation today. So remember, we just define Holm M P to be by abuse of notation. I will say just a set of holomorphic vector field, summation A G Z D D Z J, where this is germs of holomorphic map, of holomorphic function. G is equal to 1 to n plus 1, or capital N, such that real part of Z restricted to M is a vector field of M. Okay? Vector field on M, which means that at each point it's tangent to M. Okay? And remember, M is always given by the set of coordinates ZW, such that ImW is equal to phi of Z, Z bar real W. Phi of 0 is equal to 0, and d phi of 0 is equal to 0. Okay? And now I will compute for a special, I will take a very in situ, I will say in situ, and I will compute, you will see the last final lecture why. So in situ you have coordinates Z, W, and any M can be written locally near 0, like in W is C, Z, Z bar plus higher order term. You can always write locally your hypersurface. And remember, M will be, no, just smooth. And now, for the purpose I will explain the last lecture, I need to compute, you will see why, this is M, say it's M0. You just ignore all the higher order term, right? So I will compute LM0, 0. That means I will compute whole M0, where M0 is given by ImW is C ZZ bar and nothing else. Okay? And I will try to understand what is the dimension of this guy. We already saw that DDW I compute for you yesterday. We compute that this guy is in whole M0 because the real part, which is DDS, is tangent to that. There is no S, so it's tangent. And we also saw that the grading element, the Euler field, given by 1 over 2 Z DDZ plus W DDW, if I take the real part of this guy and I restrict to M, it's also tangent. Okay? So we know it's at least at dimension real 2. There is 2 guys. Okay? So what are the other elements? A way to compute in a good order is to give weight to the variable. So you see you have the Z variable, the tangential variable, and you have the W variable. So you give the weight to Z, I will give the weight 1 over 2. And to the variable W, I will give the weight 1. Also to S plus IT. S, I say it's weight. And if you look at that, so M0 is given by ImW is Z, Z bar. Z has weight 1 over 2 times Z bar. It's 1 over 2 plus 1 over 2, and you recover the weight 1. That's why we give this kind of weight, right? In the literature, it's also common to see that Z has weight 1 and W weight 2. It's just a choice. You can normalize as you want. Okay. And you give to the derivative what will be the weight. You cut by minus 1 over 2. So the weight of this guy will be minus 1 over 2. And ddw, you give the weight minus 1. So this guy has, what is the weight of this guy? It's going to be minus 1. What is the weight of this one? You have z, weight 1 over 2, and you just, so it's weight 0. OK. You see it's homogeneous weight 0. So the idea to compute my Helm M0 is to decompose into weighted gradient components, because you have a weighted homogeneous polynomial of weight 1. You ignore what could destroy your stuff. OK? So it's enough to look at how many graded components you have. What is the smallest one, by the way? Can it be less than minus 1? No. So you start with component minus 1. And then what is the next one? It's going to be g minus 1 over 2, right? And then g0. And then 1 over 2, g1, and possibly a lot of them. That's a big question. How many are there? Because you want, as Mike said, in fact, it's finite dimensional. So at some point, you have to show that it stops. And that's exactly the case. This is really the baby case I'm doing. You know, I take C2 just to give you an idea of how you do it. So that's a method like that. So you are sure you don't forget anything. Here, what is a dimension? So we will be, you know, I hope I will have time. I will compute completely this one, and completely this one. And after, we will see that there is an algorithm, there is a theorem behind to compute the strictly positive weight. And is somebody knowing until where it goes? It stops where? Somebody knows? In fact, there is nothing after that. It stops at 1. This is a hypersurface case. It's more complicated in higher codimension. So let's do it. Let's compute very easily. G minus 1. We already have a candidate. So I will do it. So it's for G minus 1, it's A times ddw, right? There is nothing else. You cannot describe another thing, right? So is A in C or only in R? So you have to compute the real part of this guy. So it's A plus IB times, and you apply, A ddw apply to my, what I write like that, minus ZZ bar. What is it that? It's A 1 over 2I, right? And this guy plus E bar minus 1 over 2I has to be 0. That means what? That means that A minus A bar is equal to 0, so A is real. OK? So what is the dimension? The real dimension of this guy is then, the dimension of G minus 1 is what? The real dimension is 1, right? And it's generated by the guy here. OK? Now you go to the next possibility, which is what are the vector field of weight minus 1 over 2, right? Where is it? I erase it. No, it's here. How can you write them in a general form? What is the description of them? So in the DDZ, what can you have? You have always DDZ and DDW. If you had more Z, it will be a mess. So to to expect something which is of weight minus 1 over 2, what do you put in front of ddz? What are the possibilities?
Just a number.
A number? And here, what can be? What can be the possibility? A constant times what? Z. Because if you put any W, it doesn't work. Okay? And you do the computation, I'll do for you. It's what is A, what is B? Is it possible to have such a thing? Because there are some hypersurface, you don't have anything. So you play the same game. I'm going to do and stop at that point because after a while you will be sick of that. So what is W minus bar over 2I minus ZZ bar? What is the result of this computation? I need another. Oh, I think it's going to be okay. So what do you get? You get minus A Z bar plus BZ 1 over 2I, right? And now you have to take the conjugate, which is minus A bar Z plus B bar Z bar minus 1 over 2I is equal to 0, right? Is it correct? You just take the real part of that. And so what do you get? If I am not mistaken, you get, if you multiply by 2I, you have minus 2I A Z bar plus BZ minus 2I A bar Z, correct? Minus B bar Z bar is equal to 0. So what do you get? Is it correct? I think it's correct, multiplying by 2I. That means that all the Z bar has to disappear, so you get B, the Z bar, where are they? Minus 2IA minus B bar is equal to 0, right? And then it implies, and nothing else because it's the same, you get B is equal to 2A E bar, right? So what is the description? So you get that your guy should be of the form A ddz plus 2I A bar Z dw, right? And there is nothing else. A is complex. So what is the dimension of G minus 1 over 2? A is complex. So G minus 1 over 2 is given by all the guy of the form A ddz plus 2I A bar Z ddw. So what is the dimension of this component? It's 2. Dimension is 2. So we describe completely what it is. Then, so this is okay, we have 1 dimension, we have 2 dimension. What is the dimension of G naught? And then we will have a nice theorem to continue. Remember, in G naught, we already have one guy, which is the grading field. You remember? Is there some other stuff in it? So what are the candidates for G naught? What is the form? They have to, if in front of Z, what do I have? Where is my stuff? How can I write in a general form some guy which is in G naught? If I have ddz, what can I put here? Some AZ plus, and in front of what can I put? There is two candidates, right? There is B Z square plus C W DDW. Okay? So what are the possibilities? So if I compute it, I get minus A ZZ bar plus B Z square plus C W 1 over 2I. And I conjugate minus A bar Z Z bar plus B bar Z bar square plus C bar W bar times 1 over 2I. It has to be 0. Okay? And if you collect all the terms, you have term in ZZ bar, you have term in Z bar, etc. They have to vanish. So the term in ZZ bar, you have minus A bar ZZ bar plus B Z square 1 over 2I plus minus B bar Z bar square 1 over 2I. And you have plus C, what is 1 or 2I W minus C bar W bar over 2I. So you see that that's what. If I collect the term, what do I get for an equation? What are the equations I get? I get right the way that what is, right the way I see that B is 0. There is no contribution, okay? Because you have, this guy is completely alone, and this guy, yeah. So you have no, you see that B is equal to 0. And then you collect, be careful, we are living where? I should be careful, not you, but me. What is W on M? So you get, I have to restrict to M, right? So it's minus A bar, ZZ bar, that's okay, plus C over 2I. What is W on M? It's S plus W is ZZ bar. So what is W? It's S plus I ZZ bar, right? So I get that minus C bar over 2I S minus I ZZ bar is equal to 0. Okay? And now I collect all the terms in ZZ bar. You see, I have here, but I also have here. So what do I get as an equation? I finally get minus A bar plus 1 over 2 C plus 1 over 2 C bar is equal to 0. B is equal to 0, I know already. And I have C minus C bar is equal to 0 just by looking at the S that has to disappear, right? I have C minus C bar is equal to 0. So C is real. So C is real, and then C is real, and then I plug in, and I find that A has to be what? The real part of A has to be, see, if you complete completely, it's related to C in the way it's C over 2, and the imaginary part of A is free, right? Is it correct? If C is real, so you get here, what? The C is real, so C bar, it's 2C over 2, so 2 real part of A is C. So the real part of AC over 2, and the imaginary part is completely free. Okay? So what do I get for G0 then? G0 is given by what? If I replace, it's going to be X is of the form C over 2 plus ID times Z. This is my A, remember. I start with that. B, there is no contribution of Z square, and it's going to be plus C W DDW, right? So it was good to make this computation because just remember that W is on M, so you have to replace W by S plus the value on M. So what you see, if you put D is equal, it's dimension 2, right? Yeah. There is no. So this guy is dimension 2. And see, if D is equal to 0 and C is equal to 1, what do you recover? The gradient field, right? So C is equal to 1, it's the grading field, or Euler field. And now, if C is equal to 0, which is the order base, you get the guy, which is what? It's, see, if C is equal to 0, you get I, and D is equal to 1, IZ DDZ. And this is called a purely imaginary rotation. Purely imaginary rotation. We use the term of rotation when we are in G0 and there is no W value. You see, this guy has no W at all. This is the first, you know, when I was decomposing all that, it's the first time that you find W. That's a problem. To get, when you get higher in the component, you will get higher W. So it's an Euler field. So this is called the rotation. This is not a rotation because there is a W. Okay? Now, we could do forever these games and compute forever, but there is now something we have to use. So I will show you a very useful lemma that motivates why we take just the models. Because, you know, first I erase, and then I will talk. Remember, if you take any general M, you could, for instance, have im W, it starts nicely, which is the model, plus, I don't know, real W, Z square, Z bar square. It's Levi non-degenerate. But there is something, if I try to compute to M directly, this guy, I don't have a very, very important tool. Look, this guy, remember this guy. What is his form? dW, it's in Helm M not 0. I mean, when I'm forgetting about that. But it's, if I compute for this M, dDW, it's no longer. Because there is a T, there is a S. That, remember, that means that dDS, T minus ZZ bar is equal to 0. But if you meet a S here, it's not going to be 0. That's why we use really, this is one of the reasons, I mean. But it's very important that you have this guy. And why is it so important? I told you about field that who do not have any W. That's on purpose. Why? Now is the lemma. So we already have how many dimensions? We know that it's at least 2, 2, 1, 5. And we know that it's going to be I think you mentioned 8. That means that there is only 3 more, but why? So lemma. Let x, and now you take any weight bigger than 0, because you classify already until 0. So there should be some w, ddz plus b zw ddw. Any weight of weight, say, mu strictly bigger than 0, okay? That means that this guy is of weight mu plus 1, because when you differentiate, you lose 1. And this guy has to be of weight mu plus 1 over 2, since you differentiate. And sure, A of ZV and B of ZV, they are holomorphic polynomial. Because you take the weight, it means that you don't have to care about holomorphic function, just polynomial. Holomorphic polynomial. And some magic happened. So if you write A, I can write A ZW like the first coefficient in terms of WK plus etc. plus alpha 0z plus the bigger one, and B of ZW, the weighted stuff. Z has weight 1 over 2, W 1, so it's a weighted polynomial. And here you have, say, BLZ, WL, it's maybe different, plus beta naught of Z. It should be a beta to be consistent. So you write that. Say, for instance, W squared plus Z4. This is a perfect stuff of weight 2, right? Z doesn't have the same weight. And the conclusion is then, if K is bigger than L, the weight Y, so X is in Holm, M naught 0. I start with a guy like that. And the following guy, then, if K is bigger than L, Y defined by K factorial alpha K Z ddz is where? In Holm. If you understand the statement, what can you say about if K is equal to L? Look, this guy, there was a lot of W, and now there is no longer W. If you understand, if K is equal to L, have you a guess for what kind of field is in Holm M0? So this is the first. I have 3 different choices. Right? If K is equal to L, what can happen? I claim that Y is equal to K factorial. It starts the same. We say factorial, yeah. No, we don't say factorial in English. Facultate, no, that is in German. And what is here, you think? No, what can, so it's L factorial, BL of Z dW is in Holm M00. Do you start to see what happens? And there is no W at all. They are all rigid. It said when there is no W, we say it's rigid. And if K is less than L, then the winner is L factorial BL of Z dW is in Holm M00. Why? Why is it so? You see that it's like a differentiation. It's a differentiation. And what is the key information? You know that DDW is in your stuff. You take bracket. You remember, if I have two fields, as I told you yesterday, this is a sub-Lie algebra. That means that if you have two guys, you can bracket it and you are still in the same. And what is the weight? I mean, that is not important. So you can bracket what with what? If you bracket DW, prove. So you take your guy. Where is your guy? Here. If you do DDW x, what will happen here? This is in Holm, right? Okay? So if I do DDW, I'm going to write the stuff so you can see more. It's A alpha k z vk ddz plus b plus yeah. What happened to that? If I bracket it at 0, I mean at what happens? There is a constant in front. So what is the only thing which matters? It's when dW acts on the coefficient, okay? And if I go reverse, there is nothing to do because it's going to be 0. There is no. So what is the result of this guy? What do I get? It's like differentiation with respect to W. So I get K alpha Kz Wk minus 1, okay, plus blah, 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 ddz, and the same for W, plus L beta L, right? Okay? But I can, since it's in all M0, I'm allowed to repeat it until I get to the last, to the higher power, okay? And then finally, depending of who is the biggest one, I get rid of all the W. And they are in whole M0. That's a very crucial argument. That means that, what do you need to know? You need to know only the holomorphic vector field lying in the Holm that have coefficient with C. And then what you do, you just integrate them. You go reverse, you know. You compute this guy. We are almost done with this guy. We already have a bunch of them. And then you integrate. And integrating, it's a better process because you describe completely, you know what you are looking for. It's not in the, no, you know that it's an integration. Look, for instance, so I guess you understand. The key point is DDW is in the model. There is no W variable, real W variable, so you can really use this guy, which is fundamental. Okay? So we have already an example. Remember the grading field. What is the form of the grading field? The grading field is given by its of weight 0. It's of weight 0. And it was given by 1 over 2 z ddz plus w ddw. Am I lying when I say that what do I get when I differentiate with w ddw? What is the result of that? It should be in Holm M0, but if I differentiate with respect to W. There is nothing here, and I get the guy who is living in G minus 1. Okay? So that means that this guy has already one integration. And in fact, and it's an exercise, unless we have time after, you can prove it's not difficult, because you know always that I will do a little more of this, but you know that W, when you restrict to M, you have it's S plus I ZZB. So, and by looking at, the different power. So, just to let you know that. So the consequence is, and I'm going to write that. Sure, you don't need two variables to do that. I show you for C2, but you can do that not only for ZZ bar. I took as a model it's ZZ bar, but you could have a polynomial of degree M and play the same game. The weight will be what? If you have a first polynomial which is not of degree 2 but of degree m. So what is 1 over m? You give 1 over n and w1 and you play the same game, and it's going to be very complicated. I mean, it becomes to be very, very complicated. That's why I'm doing only that. Okay, consequence. And it appears, I think, already. I don't know exactly when this. I don't know if Moser has already this argument. I'm not sure. But anyway. So consequence. It is enough to compute all the called rigid fields. The rigid fields are the fields which are independent of W. All the rigid fields, that is, whose coefficients are independent of W. And then integrate number of times. And that's a very magic stuff that, something very nice happened. Okay, so let's back to my description. So we have G minus 1. This is a perfect rigid field. Then we have G minus 2. I don't remember exactly what it was. It's minus 2 IA bar, right? Or plus? I don't want to do. It's 2IA bar. And then G minus 1, 1 over 2, G0. But what's next? What is the next possibility? The rigid one, you could have something of the form Z cubed, DDZ, there is no. So what do we have to show? Because we know that it should be 8. So we first compute what happens if you have a rigid vector field of weight bigger than 0, because we computed until 0. But here, what happens? So take your favorite mu and z. So what will be the form of such a field? If you take a mu bigger than 0 and rigid, what is his form? What can you have? Rigid. So you have the power of any power of k bigger than 1. DDZ plus b with another power, not the same power, because DDZ and DW do not have the same weight. Okay? So what will be the equation to be homogeneous? This is of weight k over 2 minus 1 over 2. And this is of weight u over 2 minus 1, right? So you should have this equality, okay, to be homogeneous. And this will be of weight u over 2 plus 1, right, is equal to the weight mu. Because to be of weight mu, you increase by 1 since you subtract 1. And now I will do that for you. I don't know how much time I have. I put my phone.
Still, 17, 18 minutes.
Where is my phone? Oh, here. Oh my God, already? Okay, let's do it. We have enough time. So I tell you, you think there is a lot of them just by intuition? You think it's going to be some? If k is bigger than 1, what do you think? What is your guess? You think there can be 1? There is no. That's a good news. There is no. This is called the generalized rotation or the exotic rotation because this phenomenon can happen if you are in the Levi degenerate stuff, in the finite dimension, in the finite type hypersurface. But when you are in Levi non-degenerate, there are none of them. Why is it so? So I apply A zk d dz plus b z u dw to my w minus w bar over 2I minus zz bar, and I will take the conjugate, add. So what do I get? Minus A zk z bar, right? Plus b 1 over 2I, right? Now I take the real parts, I add, so it's going to be minus A bar, z bar k, z plus b bar, z bar u minus 1 over 2I is equal to 0. And k is bigger than 1. So what happens? This guy can never compensate with anybody because this guy is not available and they are different. So the only solution is A is equal to 0 and B is equal to 0. This is the good news. And it's the same phenomena if you take Levi non-degenerate in Cn. But if you lose the non-degeneracy, then everything goes down. OK, that's good news. That means that we have to integrate only g minus 1, g minus 1 over 2, and g naught, and see what happens. And I will give you as an exercise, because it's not really complicated, but we can discuss about that. The final result to finish, to complete the dimension is the following. Oh, okay. Sorry. Like a theorem, but yeah, it's a theorem. So you have your g minus 1. You have g minus 1 over 2, where you describe everything. And this is rigid. There is nothing rigid higher. G minus 1, the guy here, A dw, we know that it integrates one time because we have the Euler field. But in fact, you can show that it's integrates 2 times and nothing more, and no more. Integrates only 2 times. And I will give you, show that it's G1 because if you integrate minus 1, 1, it's going to be 0. And another time, it's going to be 1. Okay? So G1, which is a 2 integration of dw, is given by A times w squared dw plus z dw ddz. Or if you prefer, if you put 1 over 2, 1 over 2. That means, am I correct? Because if I differentiate one time, I should recover the grading field. Is it correct? Yeah. Because if I differentiate one, I will have w ddw plus 1 over 2 z ddz, which is the Euler field, you see? It's very easy. But if you try to integrate this one, there is nothing. Because you get this kind of, power, they cannot compensate anymore. That's the point. So what is the dimension? I told you it's A is real. So what is the dimension of this component? It's generated by just one element. So it's of dimension 1. So we have 1, we had 2, we had 2, we have 1. What can happen? That this guy, the next one, g minus 1 over 2, this is also a result. The element g minus 1 over 2, I mean the element of g minus 1 over 2 integrates one times, only one times. Integrate, there is 2 guys to verify, remember? Because it's of dimension 2. Integrates just only one time. And it's always the same obstruction. You just collect the power and you see that it doesn't work. One time. So if you have 2 dimensions, you can try to think. G minus 1 over 2 is of dimension 2. If you integrate both of them, it's going to be also of dimension 2. You can show that it's the dimension of the integration, which will be G1 over 2, because W has 1, so minus 1 over 2 plus 1 is going to be 1 over 2. So here there is a G 1 over 2, and it's going to be of dimension 2. And it's if you differentiate this guy, you get here, okay? But now there is one I didn't talk about. There is still one. And there is no integration. The rotation never integrate. And G0 never integrate. The rotation are the weight 0, do not integrate. And now you are complete. 2, 4, 6, we have our 8-dimensional stuff that Mike was talking about. Just for C3, you know the dimension? If you go to C3, here I took Z. If you have Z1 and Z2, you do the same game, and the dimension is 15. Yeah, and after I don't know anymore.
N times N plus 2.
N times N plus 2, yeah. N times N plus, yeah. Exactly. So you see, what does it mean? Just, I have 2 minutes. That's, oh yeah.
Oh, still 10 minutes.
10 minutes. So you were able to compute this Lie algebra Holm M0, and you know exactly how it looks. That's fantastic, because plus G minus 1 over 2 plus G0 plus, there is something here, and there is something here. And that's it. So what is the possible maximal degree of the coefficient, which are polynomial, by the way? What is the polynomial degree, the maximal one? Here, it's constant, it's linear, it's ZW, right? And here it's W square. I told you, I show you here. That means what? That you don't have something of degree 3. It's only up to degree 2. And it's exactly why, we will see tomorrow in the final lecture, why, when you take any M now, forget about the model, take your any M, not M0, you will see that if you compute the biholomorphism map between M where you allow perturbation of the ZZ bar. Maybe you know the theorem. Any biholomorphism is determined by 2 jets. The reason it's exactly encoded here. This is degree 2. You have nothing else. It's exactly the reason. So maybe I will just state the theorem and give maybe the motivations. I have 5 minutes.
A bit more.
Maybe people are hungry. Maybe you prefer to. Just to give a motivation of this finite jet determination. If I find my notes, yeah. The motivation is given by the theorem of Cartan. Maybe you talk about this theorem in your.
Yes, we mentioned the fact that we have one jet determination.
Yeah. So maybe can I recall? Maybe it's a theorem of Cartan. Back to 1931, I guess. And it's not in the hypersurface. Hypersurface is the boundary. Cartan cares about domain. So we have let omega in Cn be a bounded, connected, open set containing 0. And you give yourself a holomorphic map, self-map, like that. Holomorphic map, satisfying f of 0 goes to 0. We will be in this case tomorrow. And the derivative, holomorphic derivative, is the identity, which means that there is a biholomorphic map, where E is the identity. Sure. For instance, give me a map, your favorite map, which goes from omega to omega, with identity as a differential, f of z is z, right? You know, there is an example, f of z is z. It's exactly the conclusion. There is no order map. Okay? So it's very rigid. You know that there is one, and in fact, all the maps are the same, and they are the identity. F of z is equal to z. That means that when you give first derivative, you have completely described your holomorphic map. For the boundary, you need more. You will see tomorrow that one derivative is not enough. You need to go to 2 derivatives. If you give yourself 2 derivatives, then you know completely your map. And I have to say that it's no longer the case if you jump to higher codimension. This is only true for a hypersurface case. Okay? So I hope tomorrow to give you the completely picture about how this Holm M0 comes into the picture to prove completely Chern-Moser theorem, which is the theorem of Chern. Okay, thank you.